mean number of inter-arrival time. So that is nothing but the mu by lambda. Now we can define the traffic intensity, that is nothing but rho. Rho is equal to arrival rate divided by the service rate. From above you can get rho is nothing but lambda by mu. It can be shown that the DTMC is a positive recurrent when rho is less than 1. We have already made it is irreducible and aperiodic. Now we are giving the condition for a positive recurrent. When rho is less than 1, the given DTMC is a positive recurrent. If rho equal to 1, it is a null recurrent. If rho is greater than 1, then it will be a transient. That means when rho is less than 1, all the states are positive recurrent. Therefore, the DTMC is said to be a positive recurrent. Similarly, when rho is 1, all the states are null recurrent. Therefore, the DTMC will be a null recurrent. And similarly, for rho is greater than 1. So, our interest is to find out the limiting distribution. So, when rho is less than 1, the DTMC is irreducible, aperiodic and positive recurrent. Along with the condition B0 is greater than 0 and B0 plus B1 is less than 1. With this condition it is irreducible. With rho is less than 1, it is a positive recurrent. We can easily verify it is a aperiodic. Hence, the limiting distribution exists and it is unique. And that will be independent of a initial state I. Therefore, pi j will be a limit n tends to infinity, the probability of I to j in n steps. So, define the limiting distribution probability vector as a pi, which consists of pi naught, pi 1, pi 2 and so on, where pi j's are defined in this form: limit n tends to infinity, p of I to j in n steps. We determine the limiting distribution by solving pi is equal to pi p and the summation of pi i's is equal to 1. So, the first one is a homogeneous equation. Including this normalizing condition, you will have a system of non-homogeneous equation. Solve this system of non-homogeneous equation to get the limiting probabilities. We get the limiting probabilities are 1 minus psi power j, where psi is the unique root of the equation. Z is equal to the Laplace-Steeljes transform of the inter-arrival distribution with the variable mu minus mu z in the interval 0 to 1. That means first we have to solve the equation z is equal to psi of mu minus mu z, and you know what is the psi of mu minus mu z from the beta z. Solve the equation in the interval 0 to 1. So, the unique root you have to substitute as a psi, then substitute psi in the pi j, and that will be the, since the unique root is in the interval 0 to 1, therefore the pi j 1 minus psi power j, that will form a probability mass function for the limiting distribution. Note that the Q length distribution found just before a arriving customer is geometric distribution with the parameter psi. The limiting distribution which we got it, that is just before a arriving customer, the Q length distribution found just before an arriving customer, which is a geometric distribution with the parameter psi. The best computational method for determination of the limiting distribution seems to be the direct matrix multiplication to get p power n for increasing values of n until the rows can be considered to be reasonable identical. Whenever for a larger n, p power n has the identical rows, it means that the limiting distribution exists. Therefore, the best computational method is find the p power n for a larger n until the rows can be considered to be reasonably identical. It is important to note that the embedded Markov chain analysis gives the properties of the number in the system at arrival epochs. The q of t for t greater than or equal to 0, that is a discrete state continuous time stochastic process, whereas a qn for n greater n is equal to 0, 1, 2 and so on, that is a embedded time homogeneous discrete time Markov chain, and that is qn is nothing but q of tn minus 0, that is nothing but number of customers in the system just before the nth arrival. Hence, it is important to note that the embedded Markov chain analysis gives the properties of the number in the system at arrival epochs, not the departure epochs or not at the arbitrary time instance. It gives the embedded Markov chain analysis gives the properties of the number in the system at only at the arrival epochs. As pointed out under the discussion of MG1Q, the limiting distribution of the number of customers in the system at arrival epochs, at departure epochs and at arbitrary points in time are the same only when the arrivals occurs as the Poisson process. So, in the MG1Q, the limiting distribution of the number of customers in the system at arrival epochs, departure epochs and the arbitrary time points are same because the arrival occurs in the Poisson process or inter-arrival follows independent exponential distribution with the same parameter, whereas in the GIM1Q model, the embedded Markov chain results gives the limiting distribution of the number of customers in the system at the arrival epochs only. That is not same as the limiting distribution at the departure epochs, and that is also not same as the arbitrary time points. Now we are going to discuss the limiting distribution at the arrival at the arbitrary time points. Prabhu and Bhatt derived the results of a limiting distribution at a arbitrary time t. Let Pj is the probability that limit t tends to infinity, the probability qt is equal to j. So, this is nothing to do with the embedded Markov chain Qn. We are finding limit t tends to infinity, probability that qt is equal to j, where qt is the number of customers in the system at arbitrary time t. The limiting distribution exists whenever the row is less than 1, and the probability that no customer in the system in a long run, or the limiting in a long run, that p naught is equal to 1 minus rho, and the pj is equal to rho times 1 minus psi power j minus 1 for j is equal to 1, 2 and so on. So, this is the limiting distribution at arbitrary time. To determine the distribution of waiting time of a customer, we need a distribution of a number of customers in the system at the time of that customer's arrival, if you want to find out the distribution of waiting time. Replace rho by psi in the MM1 results since the queue length distribution is same. Our interest is to find out the waiting time distribution since the limiting time distribution at arrival epochs is the same as the limiting distribution of a MM1Q model. Therefore, you can replace this rho in the MM1 results by psi to get the queue length distribution, to get the waiting time distribution. Therefore, by replacing rho by psi in the MM1 results of waiting time distribution, you get the waiting time distribution for GIM1Q as the CDF of waiting time distribution is 1 minus psi times e power minus mu times 1 minus psi times t for t greater than or equal to 0. For t is less than 0, it will be 0. So, this is the waiting time distribution for GIM1 queuing system. First, we found the limiting distribution at the arrival epochs. Next, we find the limiting distribution. Next, we discuss the limiting distribution at the arbitrary time points from the Prabhu and Bhatt results. Then we have discussed the waiting time distribution. Now we are discussing the moments of queue size. The mean and variance of waiting time, time spent distribution, and its mean and variance can be obtained. Once we know the limiting distribution at the arrival epochs as well as you know the waiting time distribution, you can find the mean and variance of waiting time. By adding mean, you can find the mean of time spent also. You cannot use the mean value approach because the arrivals are not Poisson process. So, you can find out the average time spent in the system, that is E of t, will be average number of customers seen by at the arrival epochs, that is ELA, multiplied by 1 by mu plus the average service time, that is 1 by mu, will give the average time spent in the system. Since the arrivals are not Poisson processes, we cannot use the mean value approach. By simplification, you can get, already we know what is the average, what is the distribution of number of customers seen at the arbitrary, already we know the limiting distribution at the arrival epochs. So, we can find the mean from those results, then multiply by 1 by mu plus 1 by mu will give the average time spent in the system. Then you can find the variance of time spent in the system also. The first, this one, the mean and variance of waiting time. Since you know the waiting time distribution, you can find the mean and variance.